I would like to welcome our speaker of today, Sergei Gukov. Sergei, do you want to share your screen?
Yes, thank you. Just a second, let me try. This should work. You probably can see it already, right?
Yeah. We see a screen. So let me see what was the title on the, or maybe Sergei, do you want to say what your title is, right? So because here it is quantum groups and quantum curves, but maybe right? Is it the title?
A generic Q.
A generic Q. Okay, perfect. So welcome everybody, and Sergei, I give you the floor.
Well, thank you, Anton, and thank you all for coming and inviting me. So it's good to see many good old friends at this point virtually. Hopefully, we'll have this in person soon. Actually, didn't remember my title, but you're absolutely right, Anton, that it will be two stories, one involving quantum groups and the other involving quantum curves. And the goal of the talk is to bridge these two stories. So there will be certain aspects, of course, both subjects, quantization of curves and quantum groups are quite old, but there will be certain aspects that are new and interesting, and there'll be many new directions and problems to explore. So I'll be welcoming any comments or suggestions from the audience. By the end of the talk, I'll give you a very long list of things that I don't know, and hopefully many of you will either help me or figure it out, so probably do better than I. So one common thing between these two subjects will be Q. So if you're ever lost somewhere in the talk, then you should keep in mind that Q is always the same. So whichever story we're going to talk about, Q is the quantization parameter. And I think that's probably justifies my presence in this seminar. So first, I'll give you a motivation, and some of you may have already seen it, so I'll be fairly brief here, but I want to start with a simple toy problem, which is almost like child's play. So we won't use anything fancy in the beginning, no quantum algebras or anything sophisticated. It will be just a kind of calculus level problem. So hopefully undergraduate mathematics is sufficient to understand what will be motivation. And we'll consider integrals associated to graphs. So graph is a set of vertices connected by edges, and we'll consider decorated graphs so that vertices are labeled by integer numbers. So this A1, A2, and so on are integers. And to every such graph, we'll associate an integral. So the number of integration variables will be the same as number of vertices. So in other words, for every vertex, there will be an integral to do. And I have to tell you how to define this integral in terms of data of this AIs and the connectivity structure of the graph. So speaking of connectivity structure of the graph, it's convenient to introduce the adjacency matrix, which is matrix of size, in this case, 9 by 9, because there are 9 vertices. And every time we see an edge between vertices I and j, let's assume that two vertices are connected just by a single edge at most, then we'll put 1 in this connectivity matrix. If they're not connected, we'll put 0. And if I is equal to j, on a diagonal, we'll just put a value of this label AI, which labels the vertex. So as a result, we get matrix of size number of vertices times number of vertices. It's a square quadratic form. So then to define the integral, I'll need to specify the integrand, and it will be very much like a typical lattice model. So lattice models will show up in several places in this talk, and this is kind of a simple one where there will be universal integrand for each vertex and for each edge. This is very common in lattice type integrable models. So for vertex, we'll associate this part of the integrand where corresponding integration variable, again, remember there is one integration variable per vertex, is x minus 1 over x squared. So that will be part of the integrand. And I'll introduce variable q whose power is related to the integer label of the vertex. And then for each edge, edge connects two vertices, and for each vertex we have its own integration variable. So here, the part of the integrand will depend on both integration variables, x1 and x2, if edge connects, for example, vertices 1 and 2. So then the rule is simple. We basically stack everything together, namely take a product over all vertices, all edges, and top it off with a theta function associated with the quadratic form that was defined on the previous slide. So that defines the integrand. It's a huge integral because, again, number of integration variables is the same as number of vertices. So in my example on the previous slide, there were 9 of them, so it will be 9 tuple integral. So that's a serious integral to do if you're thinking about undergraduate mathematics, but it's not very complicated. And the last thing I have to tell you is what's the integration contour. It's each variable we integrate on a unit circle. So this is a nice complex integral. In fact, if you think about it, it's basically a composition of rational function obtained by multiplying all these factors that I mentioned earlier with a theta function. And theta function is what you think it is. It's defined as usual as a sum over lattice, q to the something quadratic, and this variables xi to the summation integer variables and I. So theta function, as usual, has characteristics, and if our quadratic form is non-degenerate, let's assume that determinant of q is non-zero, then there will be exactly that many choices of this b that will live on co-kernel of q. So, and further, I'll assume that q is negative definite for this integral to be nice. I'll relax this assumption very soon, but for the starters, let's assume that q is negative definite and non-degenerate. So then what we got is a bunch of integrals associated to any decorated graph. And the goal of this motivation is to explain that this is mathematically well-defined. And in a second, I'll explain that it's not only well-defined, but easily computable. But maybe I should pause for any questions. I want to make sure that at least so far, we are all on the same page, because this is really supposed to be very, very elementary.
Excuse me, could you backtrack one slide and one more? Okay, okay, so that's yeah, I just wanted to see again what the definition of Q was. Yes, thank you very much.
It's basically adjacency metrics of the graph, or we can think about, say, graph of our friends on Facebook. Some of us have very large graphs with thousands of friends, and each time friends are connected, we can draw an edge. So this will be a graph of size 1000 by 1000. So then Q is going to be a connectivity structure of our friends, and one can ask, what is the value of this corresponding integral in that case for?
So there's self-adjacency is weighted by these.
Exactly.
Yes. Just a small technical question. So between two vertices, one can only have one edge. Is it right?
Yes, that's right. And one can generalize it. In fact, we'll do shortly, but soon I'll say something which will make it clear that one is always enough. In some sense, doing more does not buy anything. But we'll have to see why that's the case. Yes. For now, let's assume that at most there is one edge. So that's indeed, and unfortunately won't give interesting generalizations. But another remark maybe I should make is that, yeah, and as I mentioned, we'll assume that Q is negative definite, so we'll relax that too. But more interesting generalization, which is not obvious from this picture, is that here I'm drawing a graph which doesn't have loops. But it actually is interesting to introduce pi1. So take graphs with loops. So that will buy something new, and that's important, and that's possible. So that's perfectly fine. So, but again, for simplicity, we may not want to do this. Okay, so let me actually, when I give this talks, I like to do this experiment. So I'll stop sharing my slides. I hope that's okay. And I'll actually illustrate this calculation right in front of your eyes. So we play with this a little bit and see what kind of integrals they are. Because after all, if I give you the whole set of integrals labeled by decorated graphs, it may be useful to practice and see what kind of objects they are. So to everyone in chat, I'll share a Mathematica notebook with which I'm going to play now and try to compute these integrals. So as I try to explain, everything is very well defined. So and in fact, these integrals are not so complicated. So since there are complex integrals with very nice integration contour and convolution of rational function and theta function, one can basically try to do these integrals using residues. And that's actually what this Mathematica code does. So there is no point where it does integration. The code is very short. And what it really does, it basically computes the residues. So that's, I mean, of course, you can try to explore it analytically and you'll quickly come to the same conclusion. So me calling it an integral is a little bit overkill. So it's a really problem for undergraduates because it's extremely simple version of multiple complex integral. But anyway, without further ado, let me walk you through this computation. So in this code, you can put your own favorite graph. So it could be thinking diagram of E8 or 1,000 by 1,000 vertices connected, expressing connectivity of friends on Facebook, or something like this, which is a first non-trivial example. So I'll ask Mathematica to evaluate it. And it quickly does it. So first, there is some input that shows what the graph looks like. In this case, it has 4 vertices. It computes various basic information, such as this matrix Q that we introduced, its inverse. If we care about definiteness, here are the eigenvalues, so we can check if it's negative or positive definite. And after quick computation, here is the answer. So the answer is an expression in Q. Well, that's sort of obvious because we had a bunch of integration variables xi, but they are being integrated out. And then there was q coming through theta function and also in various factors, and that's what the result depends on. So it's an expression in q. And what do we see? We see that it's a power series such that overall power of q is fractional. Here it's square root of q, and the rest involves q series with integer powers and integer coefficients. So that's the structure here. So we're already learning something about it. So let me take this answer and save it. So I'm going to copy it here and perhaps increase the size a little bit. Okay. The reason I want to do this is now I'll try the computation for a different graph. So we see what the answer looks like. So let's explore how it depends on the choice of graph. So I'm going to add another vertex. So here the vertices are 1, 2, 3, 4, 5 now. I'll have to add the corresponding label. So let's do something like this. And I'll ask Mathematica to forget everything that happened a moment ago and evaluate things again. So before we look at the answer, let me first note that now it's a completely different integral. We have now 5 vertices in a graph, and their labels are different. I made some changes. So it's a priori completely different problem. So if it was on calculus or complex multivariable calculus exam, this would be a different problem compared to what we did before. So it's just a different integral, period. But let's look what happens. So here is the new answer, and here is the old answer. And you can see with the naked eye that they are simply the same. So all the terms are exactly the same. So what happened here is that we computed the two different integrals, but got the same answer. So that means that what we introduced is not an invariant of a graph or integral associated to a graph, but rather integrals associated to some equivalence classes of graphs. So there are some equivalence classes such that for different graphs, you get the same answer. And we can continue experimenting with this. I sent you the Mathematica code. You can play with this or even write a better one on your own. In the meantime, I'll go back to my presentation.
Excuse me, please. Yeah, before you continue, may I ask, the fact that all the coefficients there are plus or minus 1, is that significant? Is that also something that will happen for all for graphs? Or
that's a very good question. It's a good observation. So here there are a couple of things that will persist no matter how complicated graph we take. For instance, if we take a graph with hundreds of vertices, it will always be the case that powers and coefficients are integer, and this overall power is something fractional, but coefficients do not need to be plus or minus 1. So that's just simplicity of this particular example. So in fact, it's easy to make a modification. I'm not sure if I want to do it in real time in part 2 to save time, but I think the version of the code that I shared has already one of the examples in there that demonstrates that coefficients may be any integer numbers. So, but the good observation indeed. So some things will generalize, some won't. And what we have seen, by the way, any other questions about the integrals? So what we have just seen is an example of a so-called 3D Kirby move, or also known as Kirbyneumann moves, due to Rob Kirby and Walter Neumann, which come from three-dimensional topology, and this is something you can find in textbooks on Kirby calculus. So in particular, the move or modification of the graph that I made was one of the top moves where there was a vertex labeled by something. It didn't matter what the something is. Let's call it A, some integer label. And we add another vertex connected by an edge. And here the point is that the new vertex can only be labeled by plus minus 1. And accordingly, we change the label of the previous vertex. Analogous rule exists if edge is internal. So if there are two vertices connected by an edge, again, which is fairly generic situation, any graph, of course, has this, we can insert a new vertex and a new edge, and again, label things by plus minus 1. So these moves are called blow-up moves. And again, that has something to do with topology. And there are a couple of other moves. So altogether, these moves basically tell us equivalence relations on different ways of constructing three manifolds. So this comes from the subject of topology, and I'll get to this in a second. But first, let me summarize now some properties of these integrals. So I gave you a definition, and now I give you a theorem which summarizes some of the properties of these integrals in bullet points. So first, it's easy to check, say using a ratio test, again, these are not too complicated integrals, that the expressions we get are always convergent power series in Q inside the unit disk, but not on the boundary, not when absolute value of Q is equal to 1, but if it's strictly less than 1, then it's a convergent series. So here I also make a remark that these labels, which took values in co-kernel of adjacent symmetrics from the three-manifold point of view, now we should start thinking about these graphs as representing three manifolds because connection to topology started showing up. These are same as elements of first homology with integer coefficients, or better yet, spin C structures. If you don't like spin C structures, think about them just as elements of H1, because these two sets are isomorphic, though not canonical. Now, another property which is easy to show is that the resulting integrals will always have integer coefficients. And in fact, the structure that we saw will persist no matter how complicated the graph is. We also saw, and one can actually show this just directly now by taking the definition and analytically manipulating the integral, that they're invariant under this Kirbyneumann moves. So this this bullet point is actually very important, because what it means is that we defined invariance of three manifolds. Like I say, these graphs represent three-dimensional manifolds, and these Kirbyneumann moves are expressing equivalence relations. So the structure or the strategy for constructing invariance of three manifolds is often to associate something and then show that it's invariant under a certain set of moves. These are analogous to Rademeister moves in the case of knot theory, or Markov moves, braid moves, if you think about, say, braid presentation of the knot. So in that case, to define something like a Jones polynomial, we have to first give a rule and then demonstrate that it's invariant under a certain small number of equivalences. So in the present case, these equivalences are exactly these Kirbyneumann moves. So finally, you can ask, have I seen this Q-series somewhere? Is it related to anything we know? And as far as we know, the answer is no, this is something new. But in the limit where Q goes to root of unity, it does reproduce some quantum group invariance of three manifolds that are obtained from quantum groups at roots of unity. So that's already a first hint why we expect, or why you would naturally conclude, that whatever this invariant is, it's associated to quantum group at a generic Q. Because when you take Q to root of unity and ask what this invariant does, it relates to more familiar invariants produced from quantum groups at roots of unity. So what do the graphs have to do with three manifolds? Well, here is the explanation of where it all comes from. So the theorem of Licorice and Wallace says that every connected closed-oriented three manifold can be obtained by integral Dane surgery. And these Dane surgeries are made on knots and links in a three-sphere. So here is an example. And in general, knots and links involve fairly elaborate knottedness and topology, but if a link is made out of unknots, simple circles, which intrinsically are not knotted, then all this data can be nicely summarized in terms of the graph by replacing each connected component by a vertex. Each time they're linked, we draw an edge, and that's basically the graphs that I showed you before. So in fact, from this point of view, the integral that we had is a surgery formula for this Q-series invariant of a three manifold.
Sergei?
Yeah.
What are the A's now?
Right, the A's, yes, thank you for the question. The A's are integer surgery coefficients. So in this theorem, in general, Dane surgery allows constructing new manifolds by performing Dane surgeries on knots and links with rational surgery coefficients. But this theorem says that just integers are enough to recover any three manifold we can imagine.
So the surgery coefficient is what? Is some is how you make a regluing with surgery?
Exactly, yeah. So each link component has, once we excavate its neighborhood, has a boundary which is a two-dimensional torus, and self-diffeomorphism of a two-dimensional torus is PSL2Z. So we have to specify PSL2Z 2x2 matrix, but it's uniquely specified by, say, upper two elements by kind of Bézout's theorem, and that's going to be rational surgery. So if two elements are P and Q, we'll call it P over Q surgery, but this theorem says that we don't need that, only integers are enough, which means that we can consider matrices diffeomorphisms of the form P in one slot and one in the other slot, and something in the two remaining slots of the two-by-two matrix. Thank you. Yeah, that's a good question. So from this theorem, it's clear that, of course, not every, these graphs do not cover all manifolds, so we need to introduce individual knottedness of various components. For example, I can replace this leg of a nicer link by something that's called figure-8 knot. And as you can expect, there is analogous definition of this invariance where you now modify the part of the integrand that depends on the corresponding variable x. So here, everything was very local in this construction, what I called kind of state model or lattice type model construction of this partition function. And each link component came with its own variable x. So that's where we did the integration. So now if I want to modify, say, just that part, for example, all I have to do is to modify that part of the integrand and question where does it come from. So this will be the star of the show for me in the rest of the talk, this part of the integrand that's associated to non-trivial knot. And from here on, I'll go in two different directions. One will be quantum groups, and the other will be quantization of curves. So two subjects will address how to get this ingredient, and for topology purposes, define this three-manifold invariants. But at this point, I'm finishing the motivation, which is topological, but the rest will be more about quantum things. So I have to say that this integrand for different nodes or links is, of course, very precious for topology applications. That's very important to define this for general three manifolds. And back in 2019, it was known for some of the nodes. So here is a table of prime nodes up to 7 crossings. So there are how many? About 15 of them. And it was known for a fairly small fraction, or roughly 33%. So some of the torus nodes were available. And then in a paper with Chypre and Manolescu, we managed with hard work to extract this object using various methods called recursion and resurgence for hyperbolic knot 4-1. Figure 8 knot. But these were lots of question marks, and it wasn't clear how to proceed. But a year later, in fact, in the past 2 years, my student Sang-Yuk Park figured out how to do this computation of these ingredients, part of the integrand Fk for quite general knots using R matrices for quantum group a generic Q. Again, that's what was expected. And it is basically nailed down all of these examples with question marks. So all of these question marks are removed now. And one can compute this easily for many nodes up to roughly 10 crossings. So for instance, if you want to do surgery on some 10 crossing node, there are now hundreds of those. That's what the answer is going to be like. So now this is much more powerful than a couple of years ago. So let me explain what he did. Any questions so far? Now I'm going to go into quantum group territory. So I motivated that these objects are associated with quantum groups, and we want to keep Q generic eventually. So let's start with the usual definition of a quantum group. It's defined by usual Chevalley generators, EF and K, or sometimes K is written as Q to the H. And there are standard commutation relations, which in the limit where Q goes to 1 reproduce the familiar commutation relations of usual SL2. So this is the usual quantum group. And here, these commutation relations are very standard. So when K conjugates E, we produce Q. When K conjugates F, we get Q inverse. And E and F commute to this, what's usually written as K or minus K inverse divided by Q minus Q inverse. There are different normalizations and conventions. So here I give both for comparison. Just so that whichever one you prefer, you can recognize your preferred familiar form of the usual quantum group. So this quantum group has various representations. So first of all, there are n-dimensional representations, which is precisely what Rishitihin, Turaev, and others use at roots of unity. So there are many invariants at roots of unity that I briefly mentioned one can get from this invariance at head, and those are based on finite dimensional representations. So these are just like representations of SL2 obtained from lowest weight vector by acting with E, eventually you get to a highest weight state, and by f you can go back. So the quantum dimension of this representation is defined as q to the corresponding k type, and that's becoming quantum n. And yeah, so this is the familiar structure. So quantum groups are generic. You also have more interesting representations, which as far as I know, have not really been used in quantum topology. So this is already one of the places where if you know some good applications of this now infinite dimensional representations at generic Q, especially in quantum topology or in other fields, please let me know. So I'll be glad to hear more, because this is now more relevant. And these are representations which have only highest weight or lowest weight. So here is an example of a highest weight Fermat module, where you start with the highest weight vector. Now it doesn't have to be integer, the highest weight. It can be any complex number lambda, and that's going to be important. And from this, you can generate the rest of the Fermat module by the usual ENF action, which is summarized here. And similarly, you can do it for lowest weight Fermat modules by starting with the lowest weight vector. There are also principal series representations, which are infinite dimensional, and the corresponding k types run in both directions. So you have weight spaces which are unbounded in both directions, and these are extensions of lowest weight modules by highest weight modules. Any questions about quantum group representations? So important point about this more interesting ones at generic values of Q is that they're infinite dimensional and that their weight is complex. So this is precisely what Sang-Yu Park used to reconstruct these ingredients, the parts of the integrand, by using R metrics associated with this Fermat module representations. So this is basically the same as universal R metrics. There is just some tiny small modifications due to normalization and so on. But then basically what he did, he said that let's as in a computation of, say, John's polynomial or other invariants, now try to compute this for, first of all, generic values of Q by representing knots as compositions of basic crossings, overcrossing and undercrossing, and depending on orientation, we'll use highest weight or lowest weight modules. And as a result, this FK is going to be a composition, basically trace of as many R matrices as crossings in our diagram. So here, again, there are many details you can find in his papers, and there are some clever tricks how to deal with highest weights versus lowest weights and different types of knot diagrams and so on. But for purposes of quantum group story, I want to emphasize that this computation and this R matrix is actually labeled, first of all, by states. So these are i's and j's. So these are these weight vectors that we saw before. Of course, everything depends on Q, which is here generic. Let's assume that it's inside the unit disk. And it also depends on complex weights. If they are exponentiated, then x is basically q to the lambda, and y is another complex parameter, which is q to the lambda prime for the other strand. So what's interesting here is that this R matrix depends on continuous parameters x and y, and these are not the usual spectral parameters that one encounters in R matrices with spectral parameters. So this is not Baxterization yet. So that's one important feature of this approach. Similar R matrices appeared and are used for various other problems. For example, Murakami, when he was studying Alexander polynomial and its generalization, used so-called colored Young-Baxter equation. So here you also have R matrices with various continuous parameters, but here U and V are actually exactly the spectral parameters. So these are, again, as I try to emphasize, these are not the same as X and Y. So X and Y are complex weights, whereas here U and V are spectral parameters. There is analogous closer to what I had on a previous slide, object comes from holonomy Young-Baxter equation that was studied by Kashaev and Reshetykhin, and this is indeed much more in the spirit of what I had on the previous slide. In fact, here this complex or non-trivial labels, continuous labels of different strands take values in a group. So if one specializes them to Cartan, then indeed one can connect it to this X and Y that I had on the previous slide that Park used. There is also dynamical R matrix due to Felder, Ettingov, Schiffman, and many others. And that also has continuous parameters. So one can naturally ask what happens if one plays this game with close cousins of this R matrix that's a new Park used, namely these other R matrices. So that's basically, I'll try to give an answer or candidate for the answer to this question by going to quantum curves. So at this point, I'll switch gears and go to the second subject, but this is lightning review of how quantum groups, especially a generic Q, enter the story.
Sergei?
Yeah.
Just one question. So indeed, those dynamical Young-Baxter equation, right? It does involve various intertwiners between Verma modules. So is it going to be just this dynamical one that you're going to use, or not really? You would modify it in some way? Because yeah, sorry. Yeah, go ahead.
Honest answer to this question is I don't know yet. So currently we have a project with Boris Fagin and Kolya Reshetykhin where we're trying to sort it all out in detail. But so there are two versions of the answer. One is very superficial, and then that answer will be yes. That basically variance of all these R matrices is what will appear next. So they can be put in the same package, but they will of course in the details, and that's what we are sorting out, and it's a beautiful story. So the answer is somewhere halfway, probably.
Okay.
I apologize for not giving you crisp either yes or no, but.
Okay, thank you.
It's definitely yes, and my goal is definitely to encourage you all to think about it. So yeah. So this is a prototype where it works, and again, in this introductory part, I also explained the topological meaning of this object fk. So now what I want to do is to encourage you all to do the same, first of all, for different representations here, and use just this universal R matrix, say with different representations such as principal series, for example, or other apps, or close cousins of this form. And at least for some of them, namely this last two, I can also explain how the first one comes in. What we're going to find are close cousins of this object. And it seems that all of these close cousins are unified in the same picture. So this is in some sense, I know this is a very maybe slightly higher level, not at the level of calculus as I started in the beginning conclusion, but to me it's most exciting that there is apparent unification of some of these subjects in one unified structure where they will appear essentially as different sheets, as different branches of something more universal. So that's what I'll try to explain in the second part, or this third part of the talk. So the main part, or this last part, is based on recent paper with various authors, Tobias Ekholm and some of my students, and Marko Stosic and Piotr Kucharski and Piotr Zukowski, where we studied old problem, quantization of curves, in fact, related to some of these knotty problems in topology, and found something interesting. Here, surprise is that usual quantization type problem, which may again sound a little boring and old, as I'll discuss it in the next few slides, will suddenly lead us to quiver type structures. So these are also algebraic structures. quivers are basically very much like graphs that we discussed before, except that now vertices or edges are oriented and multiplicity is important. In the first part, multiplicity was not important, that some of you suggested, because of the Kirby move. So we can always resolve everything so that we get rid of it. So here it will be important. And a question that I want to pose to the audience is, other instances of quantization problems where quiver actually encodes the data of the corresponding wave function or something like that, that's byproduct of quantization. But let me explain it more slowly. So in the same context of knots or this quantum group invariants at generic Q, one can approach them from the looking glass of SL2C Chern-Simons theory, which perturbatively was developed long time ago, but essentially the point now is that this Z hat, the object that I introduced in the beginning, is supposed to provide non-perturbative definition. So let's now look at this through the looking glass of SL2C Chern-Simons theory. So SL2C Chern-Simons theory produces for you the following data. Given a knot and SL2C holonomy around the meridian, which I'm going to denote like this, with x and x inverse sitting on the diagonal. So these are eigenvalues, and that's the same x that we saw in the first part of the talk. One can associate the space of flat connections on a knot complement, and that's going to be a complex algebraic curve given by the zero locus of the A polynomial that lives in C star cross C star because these variables are not allowed to be zero. So we have SL2C tells us that if there is x inverse. So that's why it lives in C star. There is a natural symplectic form, and we basically get the natural quantization problem where this is like a spectral curve in some integrable system, and there is a symplectic form, so it's a holomorphic Lagrangian variety. So we should try to quantize it, and x and y will become operators, and this A will turn into a version of quantum Hamiltonian. So we'll be looking at some ground states of this quantum Hamiltonian. So this is, again, typical summary that many of you know probably even better than me of how we quantize algebraic curves. So there is this sort of trigonometric or logarithmic symplectic structure, symplectic form dx over x wedge dy over y. That means that quantization gives us exponentiated Weil algebra, which is quantum torus. And since this is a holomorphic Lagrangian submanifold, that the curve itself, it defines a state, and the corresponding state in this WKB or semi-classical approximation is basically given by exponential of integral of the Liouville form, one form, along some path on this curve. So we basically get PDQ type integral, and that's what this wave function is supposed to be. I'm already calling it here Fk because it depends on x, which is position on a curve, and quantization parameter q. So that's going to be compared to the same object in the earlier part or parts of the talk.
Do you need any integrality condition on the curve?
So in general, I don't know. So from this quantization perspective, for example, it's natural that at least for applications to this complex Chern-Simons, that this leading term leads to well-defined expressions. And what this means after unpacking is that over closed path, this Liouville form integrates to 2 pi squared times a rational number. And this, I'm not sure if these are kind of integrality conditions.
Yeah, it's K2 Lagrangian, yeah. Mm-hmm.
Yeah. So details of this condition are explained, for example, in this paper with Piotr Sukovsky, why it plays an important role in applications to topology. Sometimes when curves come from other problems, for instance, from Calabi-Yau or from integrable system, we can also try to quantize them, but I don't know as good reasons, at least in those settings, for such K2 conditions on because they may involve lots of parameters. And what happens here is that these curves, apolynomial curves coming from topology, they don't have any parameters. They have integer coefficients, and they always seem to satisfy this condition, which is perfect because that's what one needs. That's what's expected. And even with not fiddling with the coefficients, but rather changing powers, for example. So one can take this A polynomial for figure 8 knot and just replace power 4 and minus 4 by 6 and minus 6. And it's easy to see that it's not going to satisfy this condition anymore. So this is, of course, very delicate and very interesting. And I don't know analogous conditions or set of details in full glory in the context of, say, Calabi-Yaus or curves coming in other quantization problems, but probably they are. So again, I'll be glad to learn more. Good news is that here they're satisfied, and we can try to construct this wave function, starting with the semi-classical approximation and so on. And that's exactly the direction in which I want to go. So this is sort of old story. So the new story, or what we realized in this recent paper, is the following. So first of all, there is, of course, not a single ground state to this quantum Hamiltonian. There are many ground states, and there is a very natural finite set. So in general, there are infinitely many solutions, ground states, but there is a finite set of such wave functions for these apolynomial curves, which are naturally labeled by edges of the boundary, on the boundary of the Newton polygon of the curve. So that's first sort of kind of remark or observation, which—
Sorry,
yeah.
Sergei, are you saying that there are many of them which satisfy, which are annihilated by the A hat operator?
Yes, yeah, infinitely many. One has to choose suitable boundary conditions. That's right.
Okay.
Because I mean, our phase space is complex, so nothing is bounded. So in terms of, maybe I should put even Hamiltonian on quote. So there is no boundedness of any sort or positivity. So therefore, there are infinitely many ground states, but there is a particular basis which is labeled by these boundaries. So
Sergei, what are these boundary conditions? Because any toric surface which contains C star square gives you a compactification. So either preferable.
Yeah, I'll have it on my next slide. So yeah, that's so very good point, Jan. So indeed, I'll explain the boundary conditions, or at least as much as my time permits, on the next slide. But also, like I say, I want those of you who are more familiar with quantization than I am, start thinking about whether you have seen analogous situations, analogous structures in other contexts. And again, I'll be glad to learn if they are, and then basically what we can do, we can make more links, build new bridges to other things. But yeah, let me continue with this for now. So first observation is that indeed there is something nice and special about particular wave functions that associated to boundary of the Newton polygon of the classical curve. And the corresponding wave function can be written in the form which looks like this. So this is usually called quiver form for the following reason. So here it's a multi-sum over various d's, such that there is q to something quadratic in terms of this integer summation variables d. So di's are integers, that's a vector. And x is, I mean, it's very much like a theta function, x to the linear power, but in the denominator, we have quantum Poheimers of these di's. And therefore, the structure is basically summarized by, what's a key point here is this quadratic form. And this quadratic form, for example, can look like this. This is an actual picture for trefoil knot. And what you get, I mean, this quadratic form itself represents a quiver. It's a connectivity matrix of a quiver. So in this case, for instance, there are 3 vertices because it's of size 3 by 3, very much like our graphs in the beginning of the story, but this is completely different application. And the diagonal entries tell us a number of loops starting and ending on the same vertex. So here 0, 2, and 3 represent 0, 2, and 3 self-linking or loops starting and ending on the same vertex. Off-diagonal values tell us about number of arrows going between different vertices. So for example, 1 means that there is one going this way. This one means that there is one going the other way. And vertices 2 and 3 are connected by 2 arrows going each direction. So that's indeed what we see. And what we get in the result that there are these very special wave functions which are related to quiver. So these wave functions are essentially encoded in a combinatorial structure of a quiver. So that's something that was going on for a while and was studied by our colleagues such as Tobias Ekholm, Piotr, and others in their work. I wasn't even involved in this development, but here I want to emphasize that these structures represent very specific or interesting wave functions in this quantization problem. So that's going to be very relevant for us. And let me answer Jan's question now more slowly. So this was a summary. Now I'll walk you a little bit more slowly through this. So this is, again, same a polynomial of the figure 8 knot that we saw before. It's cubic and variable y, so it has 3 branches. And correspondingly, there are 3 what we call left edges of the Newton polygon on the left side. So left edge is an edge of a Newton polygon, which has a slope that that you can see if you project it to the left, for instance. So I think the picture probably illustrates it better than I say. And in the paper, we start with a very first and simple proposition, which says that there is a surjective map from the set of branches to the set of edges of this Newton polygon. So there is a nice correspondence. And these branches in topology have various names. In this case, they're called geometric, abelian, conjugate branch. That doesn't matter. What matters for me is that they're in this case in bijection with edges of the Newton polygon and the corresponding boundary conditions. So if you try to solve y in terms of x, you can see that, so that's the behavior, that's how it behaves. So basically y on each branch goes like x to the minus the slope of the branch. So that's something that easy to figure out. Not always edges are made of a single piece, so sometimes they have length 2, and this is of course more interesting from the viewpoint of this quantization problem. And even classically, if you try to solve y in terms of x, you'll find that the corresponding solution is now going to be the Puiseux series in x. And again, it always looks like x to the minus the boundary slope. In topology, these boundary slopes are also known to represent boundary slopes of so-called incompressible surfaces. So there is something intriguing. I don't know connection to these incompressible surfaces, so I just mention it in passing.
Sergei, from the point of view of Q-difference equation, does it correspond to irregular behavior of the spectral curve if I take, instead of Q-difference, ordinary differential with meromorphic coefficients? Yeah, then if my coefficient has a singularity, then the spectral curve goes to infinity when I approach the singularity. Is it a similar for Q-difference in this way?
I don't think so, but let me not give a hasty answer. I'll think about it. So let's come back to this, and after I want to give it a little bit more thought, but I don't think so off the top of my head. So that's a good point. Yeah, I don't think so. Okay, so now the punchline is that we take these boundary conditions, we ask wave functions to obey this particular behavior, and we can construct wave functions associated to these boundary conditions for the corresponding Newton polygon. So for example, for trefoil knot, this is the Newton polygon. That's the polynomial. It has 2 sides, and on each of them you can construct these wave functions, and you find this metric C. So for both of them, And it's different. And of course, the wave function is different. So you get two different answers, but both of them are written in this general form. So in the literature, this is often called quiver form. So this is, again, the same picture for figure 8 knot, where Newton polygon is bigger. So we have 3 edges, or left edges, I should be more precise. And again, the corresponding C matrix that enters this quiver description is different. It may be even of a different size, and so on.
I'm sorry, could you explain more about this technology, QFT, WRT, and so on? Why these different kind of flavors of the same theory give you something very similar, just different edges of this Newton polygon?
Let me come back to this in the question session. Right. So that would actually, a full answer would be, a proper answer would be whole talk of its own. So in this complex Chern-Simons theory, various branches were studied before. And this is like a 20-year-old history in some sense. So I can try to give a short answer, but let me come back to this after, if you don't mind. I'll be happy to do so.
All right, thank you.
Yeah, this is a picture from a paper with Chypre and Manolescu. So there we give some references and explain this. And again, I'll comment on it. Here I just told the picture to represent 3 branches for the figure 8 knot. What I want to do in the remaining 5 minutes, I started 5 minutes past the hour. So I think I'm allowed to have 5 minutes unless Eva or Anton object.
Yeah, sounds good.
So I want to point out yet another surprise. So first surprise was that quantization leads naturally to the quiver forms. So that's something, again, I think was basically around in the past 5 years or so for sure, but at least I myself did not fully appreciate it. So another surprise is that this quiver form here actually appears in a completely different branch of mathematics. So if you look at the paper of, say, Fagin, his son, and Tipunin, you'll see exactly the same formula. So it's a multi-sum over integers. You have q to something quadratic with a matrix, here it's called A, and q Heimer's in denominator. And what this form is called, it's called fermionic form of characters for some, in this case, logarithmic vertex algebra. So that's a completely different branch of math, which has to do with vertex algebras, where exactly the same type of expressions appear. And in fact, they appeared already almost 100 years ago, first in the work of Hans Bethe, and then more prominently in 80s. So Anton knows this much better than I do, because much of it comes from Leningrad School, where in studying relations between quantum groups and vertex algebras, which could be generally mathematically put under the umbrella of Kazhdan-Lusztig correspondence, if we expand the meaning of this word to explore the bridges between quantum groups and vertex algebras, then these two subjects sharing something in common. And the something in common usually is expressed in terms of R metrics, which can be seen on the VOA side as related to monodromies and Knizhnik-Zamolodchikov equation. On quantum group side, this is, or integrable lattice models, this is something that determines, for example, the weights of the lattice models or scattering of quasi-particles and so on. In particular, in this relations, one can find, so if one asks, what is the structure of the lattice model that shares, that's not necessarily described by vertex algebra, but is related to it in a so-called critical limit, in a conformal limit, then this structure is going to be precisely the relation between characters of the vertex algebra and this scattering data in integrable model, which has to do with the exact S matrix. So that's the structure of Youngian symmetry, beta equations, and so on. And this is what Zamolodchikov and others introduced in 80s. And then by late 80s, it was already a blooming subject. It was studied very vigorously by many groups, so including Leningrad School. So again, Anton definitely can say a lot more about this than I. Also by Barry McCoy. So there was a Stony Brook team who worked on this, and for example, by using different descriptions of the same system related by bosonization. So Berry and collaborators produced various Rogers-Ramanujan type identities relating this sums in various vertex algebras. And then they had many other connections, for example, of Edward Frenkel, Andras Shenis, and Werner Naumann collaborators were studying various relations. In particular, sometimes these sums are called num sums because Werner Naum studied connection between this characters or fermionic form of the characters to torsion elements in the block group. As far as I know, the name numsum means exactly the same as a fermionic form, so I'm just gonna stick with original name, call them fermionic forms. But the punchline here is that what we found in this quiver description of quantization of curves, these expressions here, and many of the practitioners of these quivers didn't even know about the fermionic expressions of these characters, which appear in old literature all over the place. So this provides yet another bridge, and deep meaning of this bridge is not known at present. It's very recent and in many ways very surprising. So that's yet another bonus feature that none of us anticipated or ordered. So to summarize, in this talk, I described certain motivated by topology, certain quantities, I call them FK, that can be computed either via quantum groups at generic Q, and there are various variants of those, which we can label by alpha. They can also be, each of this FK alpha can be given a quiver form that has to do with quantization of the curve. And then there was also this surprising bonus feature connection to vertex algebras and their characters. And if this feature persists, then there are a lot of problems that are needed to be addressed. So for example, even in the beginning part of the talk where I gave you this infinite set of integrals associated with graphs, one can ask about the following. So first of all, if this connection to characters persists, it means that coefficients in the Q expansion for any of the graph that you can imagine should go in a very special way. So first of all, if you normalize by eta, this normalization is present and I just simply dropped it, you should expect that all these coefficients are positive, or I guess it would be interesting to check if they're positive. So here I state these questions as either prove that this is true or give counterexamples. Also, if connection to vertex algebras persists for any graph in the, again, beginning part of the talk where these integrals can be computed very explicitly and concretely, it means that these coefficients have a very specific rate of growth. And again, it would be interesting to either confirm that they grow with a special rate, here controlled by this coefficient called effective central charge, or find counterexamples. A priori, actually, I don't know if any of these conditions should be true. So their violation is not necessarily a bad sign. For example, if number 2 is violated, it means that there is something derived going on if some coefficients are negative. So we'll probably need Felder complexes rather than actual modules of vertex algebras. It's still good, it's still interesting. But so far, in all cases that people have checked, it seems that both 1 and 2 are satisfied. And here I offer a bottle of wine to anyone who can settle it, even for the first part of the talk where we limited ourselves to just graphs. So that's already infinite territory to play with. And even in that case, I don't know how to either prove or disprove a 1 or 2. It's probably not hard. So that's why stated here as a nice research project. So there are lots of other questions, including the ones on this blackboard and then the ones you asked. So I would like to stop here. Thank you for the attention, and I'll be glad to answer further questions.
So thank you, Sergei. So please, questions or comments, you can either unmute yourself and ask directly or lift your electronic hand. So
yeah, Sergei, I some kind of missed one conceptual thing. So if you start with conventional Chern-Simons, yeah, you can recover the quantum group. Say if the level is integer, you can recover it at roots of unity, or you can recover it perturbatively. But only finite dimensional representations of quantum groups appears. Now, if you analytically continue Chern-Simons, do you force to consider infinite dimensional representations of quantum groups? What's the reason from the Chern-Simons point of view?
From the Chern-Simons point of view, simply, well, I guess a simple answer is that such representations exist. So when in a Reshetikhin-Turaev type construction, we are instructed basically in building something topological from algebraic ingredients. We usually sum over all representations when we do cutting and gluing. So that's a typical structure of Sergei formula. So the fact that here there is no nice way to separate this infinite dimensional representations out, that they exist, and in fact makes sense, is already first hint, probably I should say, that we should, even we try to glue two pieces, we will have to sum over everything, and that will include these things in intermediate channel. Another reason is the following, that yeah, this is something I explained in this 2003 paper in great detail, that Hilbert space of SL2C Chern-Simons is infinite dimensional. It's simply quantization of this phase space C star cross C star mod Z2, which I guess appeared somewhere here, for example, this guy. So it's infinite dimensional, and you can ask, okay, if I want to represent this very much like in the usual Chern-Simons with finite gauge group by taking states on a solid torus with various Wilson lines, line operators running inside, what shall I color this line operators by in order to recover all the Hilbert space? And again, you can quickly basically deduce that you need to include this infinite dimensional modules with complex weights. So this parameter x, which was used in the same way throughout the talk, is basically complex weight of infinite dimensional representation.
I forgot. Does it have a meaning of the monodromy or something like that?
Yeah, you can give it meaning of the monodromy. So that's exactly was perspective of this 2003 paper. So now, almost 20 years later, I want to modify the statement by saying that from cutting and gluing, it's important to include spin structure, and that's how this monodromy actually becomes a spin C structure. But this is too technical. I didn't talk about it, so I just want to give it as a word of caution so that I'm very precise about what I say.
Yeah, and maybe a small question. Your when you spoke about your paper with Ekholm and others, you mentioned these quivers. What's the geometric meaning of the vertices, edges?
You mean in a quiver?
Yeah, I mean, I know Ekholm. I don't think he will consider purely formal. So there should be some meaning, geometric meaning. It should be, I don't know, some disks with a boundary on some non-compact Lagrangians or something like that.
Yeah, that's exactly how Tobias indeed thinks about it. That's exactly right. So I'm hoping that, so this is not my comfort zone, so that's very simplistic, and I apologize, I won't be able to give all the details, and I don't think all the details are fully worked out, but yeah, so if Tobias were to give a talk, he would give a much better answer exactly along these lines, that there is some Calabi-Yau setup where embedded disks, which physicists would call BPS states, would be exactly the nodes. So that's why this quiver sometimes is called BPS quiver. I'm personally hoping there is a much more algebraic answer to this question. After all, quiver is a perfect combinatorial or algebraic structure, so I'm hoping that there is something very algebraic going on, especially this connection to logarithmic vertex algebras is hopefully not an accident. And then probably universe gives us a clue that there is something deeper going on, but that hasn't been done, of course, and that's part of the reason why I'm glad that it seems I'm encouraging you to think about this question. So,
yeah, thank you for encouragement. I'm also second Sasha's question about the meaning of these branches, how to think about them.
oh yes, that's what I promised at some point. Yes, thank you, Sasha, and thank you, Jan, for reminding. So where is this picture? Yeah, here. Right. So right, this is long story. So some aspects of it are, I think, reasonably well summarized in this paper we had with Don Zagir and others, where one can try to do semi-classical quantization of, say, SL2C Chern-Simons in different, by starting on different branches. Semi-classical means not writing it in Q variable, which is what I have done throughout this entire talk, but rather in terms of H bar, which appeared maybe on a couple of slides. And one can do it to great extent, and depending on whether, so even if we start at x equals 1, so very nice point kind of on a polynomial curve, and try to do this expansion in H bar on different branches, we'll find different things. If we expand on a billion branch, we'll find, first of all, connection to Witten, Rishi-Tikin, Turaev invariance, and also this Z-hat invariance, which I mentioned in the first part, expanded near Q equals 1, where Q is equal to exponential of H bar, and we can basically, that's where a resurgence story appears. One can do this expansion on other branches, and what one finds for this wave function is connection to generalized volume conjecture, where the wave function looks like this, and the leading term has positive real part. So this 1 over H bar term has positive real part, so it's exponentially growing if H bar goes to 0. And that's precisely the statement of various generalizations of the volume conjecture. So
I missed something. Alpha belongs, this parameter alpha, it belongs to some set. What is this set?
Oh, sorry, yes. So that's the set of either branches or, according to the statement, the left edges of the Newton polygon. Sorry.
Mathematically, just left edges of the Newton polygon.
Yeah.
So, and actually, what's the vertical axis here?
So vertical axis is y. So this is the curve branched over x plane with number of branches given by the y degree. So for example, see, this is cubic. So what it's trying to illustrate is that it's cubic on y, and that's why we have 3 branches.
And what is the?
May I join this? Yes, Sasha. Okay.
Is there any meaning to the fact that this Witten-Rishi-Tikin Turaev branch lives on, y equals to some constant? What is this constant?
This constant is 1. So there's always a branch y equals 1. It's called abelian branch. It always exists. And some of this invariants, like Z-hat, WRT, and a couple of others, they live on a abelian branch. So for them, it's extremely important to take, so sometimes people don't take into account abelian flat connections. So if you don't do this, we'll never find either the Z-hat that I was talking about or WRT.
I see, thanks so much, got it.
So,
but for other things, for instance, actually for this volume conjecture or Teichmüller TQFT, it's actually okay to even discard this abelian branch, and sometimes this is done. I want to give a word of caution that if one throws this away, well, one will not find this connection to Z-hat or WRT. So it's important to include all of them. So that's again kind of normalization choice, but it's important for certain applications.
So a billion, does it correspond to the stabilizer of the critical point of Chern-Simons, which should be U1 or something, I don't know. Or
yes, exactly. The topologic, these conventions coming from topology are the following, that if the stabilizer of flat connection, SL2C flat connection, or if it can be conjugated to maximal torus, then it's called abelian. Or in general, if it has a stabilizer of positive dimension, it would be called reducible. So in a SL2C case, the notion of reducible and abelian coincide for obvious reason, because we're just working in rank 1. Geometric means that it's very much in the style of Thurston, where we think about certain PSL2C connections as geometric structures associated with hyperbolic structure. Of course, not any manifold admits it, but complement of the figure 8 does, and that's exactly where Thurston would leave. And then there is minus the volume branch, which is where Anderson, Kashayev, and Leonid Chekhov, and then many others would leave. So that's the Teichmüller TQFT.
Okay. So basically, just
sorry,
some strata in the space of flat connections.
Wait a second. So maybe let's see whether there are some other questions, and if not, let's return to your discussion, which is very lively. So people,
Okay. So may I ask a question?
Yes, go ahead.
Yes. So Sergei, thank you for a very nice talk. But one thing that I am just really torching me is, so in the algebraic curve size, we have just 2 variables. On the quivers, we have many. What is the actual relation between these two?
Well, people who work on not quiver correspondence sometimes, if you mean number of variables associated to number of vertices, is that?
No, that's clear, but it's precisely the question that on the left-hand side, we have just 2 variables. On the right-hand side, we have as many as we want.
Sorry, I'm not sure I understand what are this as many as we want?
On the quiver side, we have as many variables as vertices.
Yeah, so first of all, it's not as many as we want, it's as many as vertices. And so that's what I was trying to clarify. Indeed, in this not quiver correspondence, people discuss this variables associated to vertices. So in this case, there would be 3 of them. In applications that I'm talking about, and I know best, all of these variables have to be set equal. So in applications to various categorifications of Homfly polynomial and other things, by the way, those quivers are slightly different. I mean, the structure is the same and many technologies borrowed, but these are not the same quivers that originally were proposed in not quiver correspondence.
Yes, but is it just occasion, or that you have as many variables in this inner part of Newton polygon as a number of quivers?
First of all, I have no idea how to relate. So quivers here correspond to very particular states, which are associated to boundaries of the Newton polygon, to these left edges. So how the data and each quiver can be different for different boundary slope, left edge. So I have no idea how to reconstruct a quiver just by looking at the Newton polygon. So that's already another good open question. And that's why I'm saying I have not really seen such quivers emerging from quantization problems. To me, this is a little interesting or surprising, I would say. Secondly, these applications to categorification of Homfly polynomial and so on are not relevant here as far as I can tell. And all variables on different vertices are said to be equal. So that's the variable x. So it's really the same variable. So that's why this has only one variable. After we quantize, as usual in quantum mechanics, it makes no sense to talk about coordinate and momentum. So we choose x and write everything in terms of x. So on the left side, there is only one variable. And on the right side, there is also just one variable because all of these guys are equal. I have no idea what it would mean to have x1, x2, x3. So, I mean, if that's your question, that's a great question.
That's my question.
Does it have a meaning on the left-hand side in terms of curve? I have no clue. I don't even know if the answer is in affirmative, but we should try. So.
Okay, thank you. More questions or comments? If not, Jan, do you want to continue with, because I caught you in the middle of a question?
No. It will take forever.
Okay.
No.
Okay.
I have some maybe small. I don't know whether it's a question or a comment. When I asked about this compactification of C star square by toric variety, I mean, yeah, you add some divisors. So I mean that your wave functions, solutions of the equation A hat applied to something equal, I don't know, say to 0, they might, they should correspond to these boundary conditions, which can be described combinatorially in terms of quivers. Like imagine that you add some curves and then you look for the intersection graph of this curve, or even more generally, you put some shifts supported on that curve and look for X groups. So then you have vertices to be curves, and X groups gives you arrows of your quiver. So such things do appear. That's why kind of they appear geometrically, but maybe if you convert them into combinatorial picture, it will be exactly what you wrote.
That's a good point. So in fact, yeah, I would love to. I know we're scheduled to meet tomorrow.
Yeah,
let's continue, because this is interesting. That's exactly in the direction I would like to see this developed or explored, because to me, this quivers that come from different edges, like this left edges, as I hopefully try to explain, are somewhat mysterious. I mean, it's clearly working, and at a technical level, I can explain where they come from, but something more geometric is definitely needed. And I think what you just suggested, even if it's not the full answer, it's definitely along the lines that I would like to see. Yeah.
Okay.
Yeah, thank you for the comment.
Thank you.
Thank you. Any more questions or comments? I got a very naive question, probably much more naive than the questions of colleagues. So you notice that those wave functions, they have a similar structure to those fermionic characters, right? So, but now I'm a bit missing. So suppose you establish even some general correspondence like that. So how do you want to use it? So in other words, do we know something about fermionic characters which would be useful for 3D topology, or do we know something from 3D topology which gonna tell us something new, potentially new about fermionic characters? Well, in which way this correspondence would be useful? Maybe you already know that, or like in the future, what's the hope? Why is it good for us?
That's a great question. And yeah, so I think there are lots of applications. So since I'm kind of more quantum topologist, I can say that for quantum topology, there'll be price of gold. Why? So this invariance fk, or I mean this f of xq or z hat that I was discussing in the beginning, I don't know if I have appropriate slide. They're meant to be, so why is this integrality of coefficients is important? Because in quantum topology, we want to categorify things. So we want to promote numerical invariance to vector spaces and have functorial operations on them, and that gives a richness of what topology can do with these things. So there was an old-fashioned or standing problem of trying to categorify WRT invariants and various others, for example, at roots of unity. The problem is that they have no integrality. They're not integers. Like John's polynomial is an expression in Q, which is polynomial with integer coefficients. But these guys were not. And Z hat is basically meant to address this question, provide something that has integer coefficients and is analog of the Jones polynomial, so manifestly written with integer coefficients, which may or may not be positive. Now, the price was that one had to introduce this pesky labels, the spin C structures. But let's forget about this for a second. So Z hat is, if it's graded trace of something homological, then by expressing, saying that this guy is also equal to a character of some vertex algebra, immediately provides a candidate for what the space is that categorifies this. Just because character vertex algebra is a trace of something with q to the L0 minus c over 24 and so on and so forth. So for the topology, this would be price of gold. So as you say, if this correspondence is established, so if this is not a joke, and even in some classes, we can say that that this Z hat is really character of some VOA, that's fantastic. That's great. So that would already give a candidate for something that's literally price of gold in topology. Going other way, I don't know. I think it's more question to you and other mathematical physicists and mathematicians, whether having wave function of some quantum system being a character of VOA is telling us what we didn't know before. To me, this is strange because I never really saw examples of wave functions being characters of VOA. So this seems interesting and intriguing enough to potentially hide clues to something deeper. But I don't know, if this bridge the other direction is as fruitful as toward topology. But it's a very good question.
Okay, thanks a lot. Any more questions or comments for Sergei? If not, thanks again for a great talk.
Thank you, guys. Thanks, everybody.
Thank you for everybody for participating in today's Global Poisson. Thank you, Sergei, and see you in a week from now. Thank you. Bye-bye.
Bye.
Yeah.
Bye, Eva. Bye, Anton.
Bye, Sergei. I'll write you an email about our students.
Yeah, Alberta is doing great. Thank you.
Okay, thank you.